A very pleasant good evening to all the participants who have joined here for the special program, Meet the Young Professor on the topic Einstein and Black Holes. So today, the GJASC Arts and Science College, Thoothukudi is very proud in hosting a wonderful program this evening. And we have Professor Savannah Sakbari, who is the world's youngest professor. He is an author too, as well as a child of prodigy, and who is the recipient of Global Child Prodigy Award from New York, United States. It is indeed a great privilege for GJASC Arts and Science College to have our Professor Savannah here amidst us with the hectic of schedule of what he is going with. So before getting into the program, I would like to request our beloved principal, Dr. S. Malarkodi, to welcome the gathering. Over to Dr. S. Malarkodi, ma'am.
Good evening. Respected guest of today is the youngest scientist in the world, the Professor Savannah Sakbari, and the most respectful Secretary of our GJASC Arts and Science College, Mr. GJASC sir, and the dear respected professors and the professors from GJASC Arts and Science College, and the program coordinator, Professor Dilipan Kumar, and all the participants who have presented here. A very pleasant good evening to all of you. Now today we have all meet here in this meeting and to have a special program, to have a special lecture to be delivered by the youngest scientist in the world, Savannah Sakbari. It is a great pleasure and it is a great honor to us, all of us, to have this youngest professor with us, and he is to deliver the lecture. And he is that means the Professor Savannah Harry is the recipient of Global Child Prodigy Award, and he is a well-known person. He is also known as the god of physics and chemistry and mathematics, and we are great enough and we are having an opportunity enough. So I took this opportunity as my privilege to welcome the youngest Professor Savannah Sakbari to this session. A warm welcome to you, Professor. And I also welcome our Secretary GJASC, that's GJASC Arts and Science College, and the professors and the Professor Mr. Dilipan Kumar, the program coordinator, and all the professors who meet here. I express my warm welcome to you. And it is our great pleasure, and as well as it is a great honor to us to have this youngest scientist, youngest professor in this world. So we are very much eagerly waiting for a lecture to be delivered by this professor. Very happy, sir, very happy. And once again, I express my warm welcome to you. Once again, a warm welcome to all the participants who have joined with us. Thank you.
Thank you, Principal Ma'am. Thank you, Principal Ma'am. It is indeed a great privilege for me to introduce Professor Savannah Sakbari to the August gathering again. Professor Savannah Sakbari is a Bengali American prodigy, an author and university professor who was born on April 9, 2012 at New York Presbyterian Queen's Hospital. Bari's father, Rasidwal, and mother, Shagita, were immigrants from Bangladesh. Bari also has a brother, Apoba. His parents noticed he began talking in full sentences at 6 months. He was able to solve mathematics, physics, and chemistry problems at 2 years old. His parents started recording his problem-solving abilities and shared his videos on social media, some of which caught the attention of the local TV channels and colleges in New York. On November 3rd, 2014, when Barry was only 2 years old, Vice President Gerald Postman took his interview. Barry's problem-solving abilities caught the attention of the Voice of America. On February 13, 2015, the Voice of America invited 2.5-year-old Barry for an interview to test his intellectual abilities in math, physics, and chemistry. Voice of America published Barry's interview on their website and twice broadcasted his interview, mentioning that Barry was the youngest interview since the birth of Voice of America in 1942. On 21st April 2016, Dr. Lisa Quaco, president of City College of New York, gave Barry the nickname Einstein of our time for his achievement on a series of tests in math and science. In 2016, at the age of 4, Barry received a letter of recognition from President Barack Obama for his accomplishment in math and science. And in 2018, at age 6, he received a letter of recognition from Harvard University for his problem-solving abilities. Bari was accepted into New York City's Gifted and Talented program later the same year. On April 24, 2018, Dr. Thomas Eastman, president of Brunswick College, interviewed Bari to learn more about his anti-terrorism campaign and upcoming book, The Love. On March 15, 2019, Bari published The Love, a book about loving all religions to promote his anti-terrorism campaign of the same name. Bengali Muslim extremists attacked Bari on 28 April 2019 in Jackson Heights while he was promoting his book. Savannah received an invitation from Laureate Kailash Satyarthi, Vice Chancellor of SP Pune University, Nitin Kalkar, and Principal of Ruya Autonomous College, Dr. Anubis Lokur, to make a trip to India. On January 3, 2020, Savannah received the Global Child Prodigy Award from Nobel Laureate Kailash Satyarthi. On January 4, 2020, Savannah was recognized as the Principal of Ruya College, Dr. Anushri Lokur. Savannah joined Mumbai University as a visiting professor of physics. On January 6, 2020, Savannah gave a book talk on his book, The Love, at SP University in front of university faculty, students, and alumni. Recently, Hollywood legend and Oscar-nominated Melissa McCarthy interviewed him at Warner Bros. Studio for NBC Little Big Shots. His interview was broadcasted on NBC during the prime time on March 8, 2020. He was the only Bengali who appeared on NBC Little Big Shots. So such a great profile is what Professor Savannah Sakbari is all about. So it is again indeed a great privilege for Geeta Jeevan Arts and Science College of Thoothukudi to have Professor Savannah Sakbari with us. Over to Professor Savannah Sakbari to deliver his talk on Newton and the black holes. Yes, Professor, you can go ahead.
Namaste, Honorable Principal of Geeta Jeevan College, Dr. Malakoti, the distinguished faculty of Geeta Jeevan College, and my fellow students here at Geeta Jeevan Arts and Science College. Today, I will be talking about black holes and looking at them from a narrative perspective. Now, when we're talking about black holes, we're really talking about relativity, because the theory of relativity, both special relativity and general relativity, is what predicted the notion of black holes. And we all know they're true now. But the people doing relativity didn't know if it was true. But special relativity was true because it predicted this existence. But when we're talking about relativity, we actually talk about Einstein. Because Einstein was the one who formulated the theory of relativity in the first place. But then, when we're talking about Einstein, we're talking about Newton. Because Newton was, for one, Einstein's personal idol, and for two, well, the theory of relativity formulated by Einstein was almost completely based off of Newton's law of gravity. Well, of course, sir, there was a huge fixation of all the things that Newton got slightly inaccurate in his design of gravity. But it was completely based off of gravity. So, the thing is, we have to start with Newton's story if we ever want to get to black holes. So, let me just start in a patent office in 1905. Well, Switzerland, 1905. So, in his patent office, Einstein is sitting at his chair. Well, he had been sitting at his chair since 1902 when his job application to be a technical expert was accepted. I don't know how he hasn't served after 3 years of sitting at the same chair, but okay, we shouldn't ask any questions. Anyway, Einstein, in April of 1905, had just published 4 groundbreaking papers. One of them was on electromagnetism, photoelectric effect, the Brownian motion, and finally, of course, special relativity. Special relativity was something that challenged the grounds of one of the most prominent scientists of the time, Sir Isaac Newton of England. Well, people obviously accepted because with slightly faulty experiments, his theories, Newton's theories, had been proven. So obviously, people got a little angry when he tried to challenge Newton, when Einstein tried to challenge Newton, one of his most favorite idols, and also one of the most favorite idols of the entire world. People were shouting, "What is this debauchery? Stop with this!" Oh, here and there and everywhere. I am not lying. 2 Nazi Nobel laureates even tried to attack Einstein. They were in physics, by the way. Don't know how they got that, but 2 Nazi physics laureates attacked Einstein with a racist thesis. That's not a lie. It's on the Scientific American. You can check it out. But the people, you can see, were obviously objecting here and there. And so, before I talk about how specifically Einstein challenged Newton's theorems, I have to first remind people what Newton himself did. Well, what Newton himself contributed to the physical world. And to do that, I have to tell you about a story from when I was 2. So basically on April 8, 2014, well, when I was 1 year old, because my birthday is on April 9, 2014, isn't it? So when I was almost 2, but still 1, I asked my dad, well, of course I wasn't very literate at the time. What do you expect the words coming out of a 1-year-old's mouth to be? So I asked him, "Daddy, can I have challenge tomorrow?" Well, I can only speak basic English. Don't ask me to do anything more than basic English when I was 1, because, well, it won't go well. Your ears will hurt. But anyways, I asked my dad if I could have a challenge. And, well, I didn't know what he said because, well, it was 8 years ago. I forgot. But he probably said nothing because next that happened was he shut the door on me and directed me to go on to sleep. So, yeah, I didn't quite know if he actually was going to give me the challenge I wanted or not. So I woke up 2 years old and my dad was calling me. Well, to where? To room 0. Everybody knew that by now in our house because in our old house, we had this little garage in the back. And what my dad did is he took the car out, he took all the paint cans out, he took, well, all the dust and the cobwebs. He actually hired a garbage man to do all the stuff, but it's the same thing. He drained out all the stuff except the car because we had to put that one in the driveway, but we would put the car in the trash bin if we could. But anyway, what we had to put in the driveway was the car, and we drained out everything else. And then our garage became what was known as room 0. Well, to my mother, it's still just a garage. But anyway, it was room 0 now. But my dad decided to make the name completely redundant by adding a blackboard, a chalk, and a chalk eraser. That means that the, room should have been named room 3 because there were only 3 objects in it, right? But anyway, I walked into the room to find something was different out here today. I saw a book lying on the floor. Of course, I didn't really take too much of a glance. And then, so there was something different on the chalkboard. This time, I decided to take a read. So, what was on the chalkboard? Well, it said, birthday challenge. Find writer of book and name of book in, 1 hour. Of course, I didn't really know what author and title meant at the time. But that was my challenge. I had to find the author of the book and the name of the book in just 1 hour. But I thought, this is easy. Why did he give me 60 minutes for this? All I had to do was climb the stool because a 1-year-old can't really do that. And then look at the cover of the book. It's that simple, I thought. Oh, how I had been bamboozled. Because turns out it was a mistake to not look closer at the book. Wherever the name of the book and the name of the author was supposed to be, all there was just blackness. I suspect my father had used black paint. But heck, I still don't know. I have no idea. But anyways, my father had used, presumably, black paint to cover all of the instances of the author's name and the book's name inside the book. And then I felt all the hope sink to the bottom of myself. I felt literally hopeless. How was I going to do this? I flipped through the pages, looking for some better explanation, when suddenly I found this weird picture of a planet, and it contained a lot of fish, because fish, of course, is the number one priority when you have a planet. You must always have fish. The solar system planets are an exception. But anyways, it had a bit of fish. I guess Newton had an obsession with that. And then it had a tiny mountain on the top. And that mountain had a cannon. The cannon was on the mountain top. And let's say that mountain top will be point V. And then, when you shoot the thing from the mountain top, when you shoot the thing from the mountain top, when you shoot the cannonball from the mountain top, then it just lands at point D. Didn't really put much effort into that. So, did ya? But then, it goes slightly farther. Lands at A. But then, it goes a bit further. And, goes at D. And, I'll show it on this iPad if you don't know what I mean. So, let me just turn you on. Hey, little guy. Let me share my screen. All right, share screen. So, share. All right, so connect. So, top screen mirroring. All right, so now you guys can see what's on my iPad, right? All right.
Yes.
So, all right. So, what I'm gonna do, I'm gonna draw the planet. So this is the planet that Newton envisioned. Of course, you need to have a bit of fish, because that's what Newton also envisioned is the number one priority of every planet. No, seriously, there were fish in the drawing. I checked later, a few years. And yeah, it was truthful. So, fish? It's a very terribly drawn fish, but please, I'm not Picasso, okay? And then you have a mountain on the top. And on this mountain, you have a cannon. So you see this? This is a cannon. It's a very terribly drawn cannon, but okay, again, I'm not Picasso. So, this cannon fires a tiny little ball. This is point V, and the tiny little ball lands at point D. But then, let's say it shoots another ball with a little harder force. It lands at point A. But then, let's say they shoot something with even harder force, and it lands at, point B. And then, suddenly, you have so much force that, it goes round and round. Wait, where did the yellow ball go? Sorry. Anyway, it goes round and round until it's in a stable orbit and it never comes back ever again. Until some alien comes near the planet and gets hit in the face. Then probably it'll be obliterated. Oh, Microsoft Whiteboard, they're always so freezy. But anyways, you may be asking, what is keeping this thing in its general orbit? Well, the thing is, this is kept in its orbit by gravity. Don't believe me? Well, let me draw the yellow trail again. All right, there it is. Because now it's in a stable orbit all around the Earth. So what's keeping it in orbit until it hits some alien in the face, obviously, is gravity and velocity. Gravity is keeping it from going too far away from the Earth. Gravity is keeping it from going rogue. And its velocity is just around the escape velocity. So any less of velocity and this little cannonball would fall down to the ground, which wouldn't be that bad. I mean, it would probably kill a few people, but hey, everything has a price. So all roses have thorns on them. By the way, look at this little Isaac Newton statue. You may not be able to see his face, but look. Keep right. Oh. So, this is our orbit. Not very beautiful, I know, but for the third time, I'm not Picasso. But anyways, velocity is what's keeping it from falling into the Earth, which I mean, it will kill some people. All roses have a few thorns on them, right? So, velocity and gravity. And any more velocity, of course, and it boosts off into space. And it would hit an alien face even faster, which would be bad for the aliens. Alright. So, that was basically the analogy of gravity. I saw that. People are still joining. Now there are 60 people in this. But anyways, now we have our diagram, and this is done. But that was when I saw in the pics, and that I realized, since this is, well, gravity, then I started to think of a certain story. A story that my father told me when I was, well, 1.5. So, what was the story, you may ask? Well, my father told me when I was laying in bed, like any babies would do. My father told me the story of if an apple can fall, can the moon fall? Basically, what my father told me is that once Sir Isaac Newton had an apple fall right next to him. And then he looked up at the sky and he saw a moon. And does the moon fall, you wonder? Well, that's what my dad told to me when I was 1, because, of course, nobody can speak English that good at 1 year old. Nobody can speak English very well at 1 year old. That includes me. But anyway, the thing is, my father told me if apple fall, can moon fall. That was what Sir Isaac Newton wondered. And now I knew. Yes, the moon is falling. The moon can fall. It just is falling right now, is the thing. How is it falling right now? And you may also be wondering, how are we not dead yet? Well, the thing is, it's the same situation as that cannonball, only much more catastrophic if it goes astray or hits the Earth. If it, goes astray due to too much velocity and less gravity, that changes the tides, that turns into long-term consequences, no more beautiful star observing, all the bad crap. And if the moon crashes into the Earth, I think you can figure out what happens after that. Anyways, it will just be like the dinosaur extinction, 10 times worse. Hooray. But anyways, that is basically what would happen with the moon. What is happening with the moon right now. It is falling. So guys, get ready because the sky is falling. That one fairy tale is true. Do you have anything to say? No, Professor Kumar? Okay. So, that was the day. Now I knew. Newton made this because he thought the moon could fall. So I knew now. The author of the book must be this guy, Newton. And the thing was, what could be the name of the book though? Because, well, I checked the clock and I only had 20 minutes left, at least according to my crappy time written back then. You don't really learn time until kindergarten, right? But anyways, now I only had 20 minutes left. There was probably actually 15 minutes left. But hey, 1-year-old brains can't figure that out. But anyway, I had 20 minutes left and I started to think, what could I do? And then, suddenly, an idea popped up in my mind about the name. I had already written the author's name. But what about the name of the book? Well, now I knew. Because, well, why else would there be an illustration of a cannonball orbiting the Earth? The title must be Cannonball. Aha! The author is Sir Isaac Newton, and the title was Cannonball. Yes? Professor Kumar? No? Okay.
Yes, Professor S, please.
I'm sorry. But anyway, now I thought I knew the title of the book. It had to be Cannonball. And then I realized I was so horribly wrong. I realized there was actually some Latin gibberish I couldn't understand. Well, now I know it's actually Principia mathematical principles. But, well, back then, 2-year-old brains can't really read Latin, can they now? But anyway, another person. How many? 63? That's a lot of people. But anyways, sorry, but that was when I figured out the name was wrong. Well, the author was all right. But what about that author? Had to do more research. Who was this man right over here? Who was Sir Isaac Newton? Well, Sir Isaac Newton, in other words, this little guy over here, was a physicist that was also head of the Royal Society. But we'll start from when he was young. He was born to a single mother, which is sad. His single mother was named Hannah Iceco, or at least I'm hoping I pronounced that right. Hey, Victorian English names are hard to pronounce, okay? But anyways, Hannah Iceco, who was Newton's single mother, who would be his single father, a wealthy, rich, uneducated farmer, ironically, named Isaac Newton Sr., had died 3 months earlier. So, well, he was given birth to by a single mother. And, well, his mother was still alive for some time. But his mother couldn't really deal with him. So, at the age of 3, Newton was given to his maternal grandparents, who, for those of you who don't know what that means, are basically the parents of your mother. Paternal grandparents are parents of your father, by the way. Anyway, so, where was I? Oh, yeah. So, Sir Isaac Newton was given away to his maternal grandmother and grandfather. And meanwhile, Hannah Iceco, who had been widowed once, had to get another husband, obviously, because that's what you do when your old husband had died. And so, she did get one. I don't quite know what his name was, but he was the stepfather of Sir Isaac Newton. Sir Isaac Newton hated him. Sir Isaac Newton well, in secret, had a list of all the sins he committed against his stepfather until he was 19. So, yeah, you can get on with how much he really disliked his stepfather. But anyways, he distinguished himself from the other school kids at an early age by building windmills, sundials. He was building everything of the kind. So he was a very amazing wonder child, even in the early stages. So yes, he did show signs of intelligence at an early age. So then, in 1665, he discovered the binomial theorem, started putting the hammers into the nails of what would be calculus. But then, later that year, something monumental happened. One day, when he was going to Cambridge, well, it was during the plague, so not really going to Cambridge. He was just basking in the sun, like any person would do, even scientists. You know, everybody has to get sunlight sometime. Not light that comes from torches, of course, but anyways, he went out in the summer light, and then he sat under an apple tree, really ripe, not rotted, ripe. And then, suddenly, what he was thinking about, well, what would be a next move? What was calculus about? What about the binomial theorem? An apple suddenly fell right next to his head. If, well, he was a normal person, then he'd probably think about the close called concussion he was about to have. Well, because apples can give you concussion when falling from the height of a tree, right? But anyways, well, instead, this guy didn't think about what could bonk his head, but rather he thought about how does this fall? Why does this fall? Then he thought, the apple could fall? Can the moon fall? Is the moon just suddenly rose over him? He ran back home because, well, nobody likes out being in the dark without torches, of course. And, well, he pondered, what was this sudden thing? What was this discovery? Well, everybody had thought, well, nobody really knew what it was. But then, Einstein had formulated, no, not Einstein, Newton had formulated the idea of gravity. What was gravity? Well, gravity was a mysterious force, not only pulling things to the center of the earth, but also pulling two things who are massively apart together. So, well, according to Newton's law of gravity, the moon attracts your girlfriend more than you, which is, well, a sad fact to think about for those of you who don't have a wife yet. But still. Anyway, the law of gravity was the thing that really still had a bit of flaws, but it was much better than any other physicist could do at the time. Who else would describe Sir Isaac Newton as a genius? Everybody. So, well, Sir Isaac Newton's discovery of gravity was regarded to be fact. And, well, yes, it was almost correct. But it still had a few flaws. So anyway, first let's talk about what gravity really did. Well, let me just drink some water. The law of gravity, or the universal law of gravity at least, said that the force of gravity between two objects, even on the opposite sides of the universe, boy, that's far. Let me just show it again. So, give me a second. 68 people, which means 67 watching me. Mamma mia, that's a lot of people. All right. So, Green mirror. All right. So now you guys can see it, of course. I tested. And what we're gonna do is we're gonna, well, draw this. So imagine you have two things, 1 and 2, that are a distance d apart. So now the thing is, we're gonna use the force of gravity, well, Fd, to find the force of gravity. The universal law of gravity states that the force of gravity, whatever it was, well, Sir Isaac Newton presumed it to be a force, but Fd was d m1 m2 over r squared. Of course, g meant, well, the gravitational constant, which is this ugly number for those of you who don't know. And so m1 is the mass of the first object, m2 is the mass of the second object, and finally we have r squared, which is the distance between the center of both of the objects. So the distance between this red dot and this other red dot is going to be r, which is basically going to be d, and then we squared that. So that gives us this equation. Sorry, but that is the force of gravity. But now, the thing is, well, it didn't really seem that good to other people. Well, not the people of the time, but let's say you fast forward 300 years, which we're going to do later, not now, later. But anyway, let's now go to the other scientists of the time. Ampere and Volta. Volta was actually doing his experiments around the late 1700s when Newton was still dead. He'll come back soon. And, well, the early 1820s. And Volta discovered the battery. You see that? Yeah, that's the battery. He didn't invent Duracell though. Somebody else did that. Well, I don't know. I don't care to Google it right now. But anyway, Volta discovered the battery. Ampere, which a few years after, he discovered what was known as current. Oh my God. And, well, finally, you have, who connected the two? So, was not only the inventor of this cool looking symbol, but he was also the man to find the relation between these two. And also make a cool looking Illuminati triangle. But hey, who can judge? It's a cool looking damn triangle, okay? So, now, the thing was, the discoveries of these three also note Coulomb, who totally didn't copy the equation of Newton. All right, let me just show you how blatantly he copied Newton. Anyways, what he did was he took this equation of Newton that we just reviewed a few moments prior, m2 over r squared. Remember this guy? Yeah, he's back. And now, what Coulomb says is, this equation looks pretty nice. Can I steal it? And then, what he did He went all scribbling over it. Forget Z. This needs to look better. How about, let's make it more friends. E. No, forget E. More friends. F. No. He called it for the electric friends. And then he scribbled over it even more. See? Forget that. That's only for gravitation. Let's make it an even cooler constant. Oh yeah, K. And then he scribbled over everything else. Oh my God. M? Ah, what horrid symbol. Q. Charge. And yeah, he basically just copied off of it. And then he said, yes, of course, my totally original equation. And that was it. So now, that was the first time the French had copied somebody. But don't worry, the French will also copy somebody else later. So yeah, that's one time that you guys got bamboozled by the French. So, now, what was the reaction of a local scientist to these three harrowing discoveries? Well, for one, Ørsted had also made his own discovery. If you don't know, it's this spelling. But he had made his own discovery. The joy of dancing in his own office to the music of these. He had changed his entire damn curriculum, obviously exaggeration, but he had changed his entire curriculum, the current, obviously an exaggeration, but still. He loved code. And what he did one day was, while he was teaching the inventions of the French, then what he did was he had left his compass. Let me just do a quick drawing of one. You should know how they look by now, but I'm just gonna do a quick drawing. So he had left his compass. Oh yeah. So he had left this little guy over here. Oh, which way does it face? Oh yeah, this way. Left this little guy. Get out. Next to a wire. And when he turned on the battery, which I'm going to demonstrate using Duracell, you're not the best. But anyways, I'm gonna put some Duracell battery over here, which we also have over here, but still, this guy. So you took this battery, and when he turned it on, the light went up as normal. But what happened was something unexpected. What happened was that this tiny portion of the compass, the needle, actually rotated. How do I rotate this damn thing? Okay, I'd give up. But anyways, this needle actually rotated, which was the surprising thing. It wasn't supposed to deflect away. He thought it would just sit there. So he thought, was there some magnetic influence? He had left his magnets at home, so no, there couldn't have been magnetic influence. So, of course, you know, if you take a magnet, and if you take a compass, then the compass goes crazy pointing at the magnet. You can see that it just completely points at the north side. It does deflect away from the south side, but still, he knew there couldn't have been any magnetic influence since he had left all his magnets at home. That it was an extremely strong magnetic field that we can't even see today in neodymium magnets. Well, then, there has got to be something else affecting it behind the scenes. And so, now he knew. These guys can generate magnetic field when turned on. And yes, I'm actually going to generate this magnetic field with a battery circuit. So DC, give me this guy, turn on 6 volts, and there's got to be the light bulb somewhere. Ah, yes, you there. And so I'm gonna turn on the light bulb. You guys should already know this, but take this on, and let me. Oh yeah, last battery to be in. Yep. So as you can see, it is generating. Mamma mia, that's a lot of current. So yeah, you see this. But now let's see what happened when we put the compass here. Well, this is deflecting. I did it with an experiment with a magnet, and it was deflecting with the magnet cord. Well, you'll see what I mean later. But this deflects even more. But anyways, this was cool. Now you knew this could produce magnetic field. So now you knew that in some way, electricity and magnetism had to be connected. But how? Well, this apparent connection, the connection that everybody knew, was brought on by Faraday with an F. Not this little guy over here, but Faraday. Thank you, Sir Isaac Newton. Bye. But anyways, what did Faraday do? Well, he started out a pretty poor man. Let me just stop sharing for a bit. He started out pretty poor. By that, I mean he literally had no education. He didn't even know how to add, how to subtract, how to read, how to write. Well, until he was 14, he didn't know how to read or write because he lived in a very poor family. Well, everybody was pretty much poor in England. But anyways, he lived in a very poor family. And so, well, what could he do? Well, he went to a church Sunday school, which isn't very good education, when he was 14, and finally learned basic reading and writing. And his education wasn't very good either. He was bearable, and he had almost nothing on his hands. So let me just take a sip of water once again. So, well, he was bearable. But then, he had an application. He had one chance to go to Sir Humpty Dumpty Humphrey Davy's class. Who was Humpty Dumpty Humphrey Davy? Well, he wasn't fat, unlike Humpty Dumpty the egg, but he was a bit strict. Unlike Humpty Dumpty the egg again, but they had similar names, so that's the only comparison I made. Right? Right. Alright. So, well, how many? Oh my god, 72 people? That's a lot of people, mamma mia. But anyways, Faraday, now being in Sir Humphrey Davy's class, it's hard to not say Humpty Dumpty. Trust me. Wait, what did I just say? Never mind. But anyways, he had just gotten accepted to Sir Humphrey Davy's class. And now he was in one of the most, famed practitioners' class, only rivaled by Ampere. So now, well, he had a lot of chemistry knowledge. Now, Sir Humphrey Davy, trust me, it's really okay. Sir Humphrey Davy's chemistry class gave him some of the most thorough chemistry knowledge that anybody in the entire world had. And so, well, Faraday was now one of the greatest, on the path to become one of the greatest scientists of all time. He applied to work for Sir Humphrey Davy. And guess what? He was accepted again. Quite a miracle. You would think this was favoritism at this school, but no. This was actually what happened. So, yeah. Faraday is now working under the elbow of one of the greatest scientists of all time, and he himself was on the path to be a great scientist. And well, so that meant that now he could do everything on his own. So, 11 years after he graduated from Sir Humphrey Davy, he discovered induction. What was induction? Well, let's take copper. You can see this, right? Well, a magnet, and let's plug them into handy little galvanometer over here. So let's take these guys off. Let's plug them into handyman galvanometer over here. Keep in mind that for small scale experiments like this one that we're doing right here, it won't work for light bulbs because light bulbs need quite a bit of voltage to generate. This generates only like 0.5 volts. Light bulb needs like 2 volts to turn on. So bear with me if you don't see any light. So anyways, this is our experiment so far. Let me just get it done. But anyways, let me. So that's the amount. I guess this will work. But anyway, I have somebody holding the galvanometer for me. So here is this, and here is that. So it's kind of hard to also. So I can't really bend down a little bit, but here. So I guess somebody can turn down the blinds because nobody can really see. But anyways, the point is when you move this magnet through a coil, I can't sew it. My hands are not free. When you move this magnet through the coil, that moves. So that's the point of this experiment. To demonstrate a galvanometer. Well, a galvanometer or an ammeter, if you're a fancy kind of guy, is, well, something to demonstrate current. So yeah, what I see on the galvanometer right now is it's like jostling at 25. So yeah, that is what induction is. Generating current using magnetic field. Or said you could generate magnetic field using current, but now the opposite was true. Mysterious, wasn't it? So anyways, that was Faraday's discovery. Which leads us to the next big scientist we will see, Maxwell. Now, just one thing. You may get confused with Maxwell and, well, somebody that bad, like a gangster, because of his large beard. But don't worry, he wasn't crazy. He was just himself. Sorry. It was natural for Maxwell to have a big beard, okay? Imagine him as Santa. Now, on second thought, Santa's an anagram of Satan. So, well, no, don't think of him as Santa. Anyways, the thing was, he had a big beard, but also he contributed 4 giant equations to science. So, Santa Claus over here generated 4 huge equations that united electricity and magnetism once and for all, combining them into a huge subject called electromagnetism. It's like marrying one person and one person, and then combining them into one person with a weird 4 arms, 4 legs, 4 eyes, everything. So yeah, electricity and magnetism were mashed together with Maxwell's equations. So, what were Maxwell's equations? Well, let's cover them right now. So the first one is electric flux, which we know to be, well, Q over epsilon naught, where Q is, you already know from his copying, and, well, epsilon naught is gonna be some constant. So let me share again. Sorry, I'm not the best with the mouse. So another person admitted, okay, no. So all right. So let's go to Maxwell's equation. So what are Maxwell's equations? Well, first one is about electric flux. Electric flux, well, is the closed loop integral of E dot dA, which is basically all the electric field that goes through a closed loop that has this certain area. So that is E dot dA, and we also know that electric flux equal to Q over epsilon naught. We already mentioned this from the copying of Sir Isaac Newton's equation. See, French! And so this was that. And that, this guy over here, is epsilon naught. Who is epsilon naught? Well, he's our little friend. He will be our little friend for years to come. And his value is 8.85 times 10 to the minus 12, which is frighteningly small for who's supposed to be your friend. But hey, I'm not the one to judge. Scientists are. Well, I technically am a scientist, but still. So, the closed loop of E dot dA is equal to, well, Q over epsilon naught, because they're both equal to electric flux. So anyways, that is the integral form of Maxwell's first equation. Sounds simple, I know, but don't worry. The second and third equations are straight up copied from, well, everybody else. Oh, the fourth one has his own addition, but chill. Oh. So the second equation, as I mentioned, is completely copied from Gauss. So this second equation, what is the second equation? Well, basically, a magnetic monopole can never exist. That means all the charges, magnetic charges in the universe, must cancel each other out. Because a magnetic monopole, which means basically one soul north or one soul south, can never exist on their own. So, no, I don't want that. Sorry. Why did it just input a yellow square on my screen? I hate you, yellow square. I also like you, so I'm going to send a like. Alright, let's delete it. Because we don't really care about it now, do we? Anyway, this is, the thing is now, the magnetic field, the divergence of the magnetic field will always be zero because there's no magnetic monopole. A plus and a minus can never be alone. Isn't that happy? We're never alone. Never. Okay, that's kind of scary. But anyway, Kirudika, how many people are there in this interview? Can somebody tell me? Somebody tell me. Alright, so anyway, this is the second equation, or Maxwell's second equation.
Professor Savannah, your mic is in mute. Can you please unmute yourself?
Oh, sorry. So the thing is, well, the divergence of the magnetic field is zero, which is straight up copied from Gauss' law of magnetism, but sus, don't tell anybody. Anyway, divergence dot B equals zero, which is also known as Gauss' law for magnetism. Now, Maxwell equation 3 is a bit trickier than the other two. But, well, let me just simplify it down and just say this. Curl of an electric field, which means basically how much something curls inside it. So think of it as this. What is curl? Well, it's like a ball curling up, except there's no ball and it's not curling up. Okay, so curl dot E is equal to B over dt. So already we're starting to see some connections between electricity and magnetism. And finally, oh my, is that 75 viewers already? Jeez. Okay, still 75. Waiting room 2, admin. That's 75 participants. Jeez. 75 people watching me? Can't handle that now, can I? Anyways, this is our equation, Maxwell Equation 3. And now what is number 4? Number 4 is a little tricky, but I can provide a detailed explanation of it. Well, so first, what I'm going to do is I'm going to draw 2 wires, A and B. Pick your point. I mean, now what we do is we're going to draw a loop. And we're going to just put some highlighter inside it. Great recipe if you want to be a top chef. So now put a little soap layer inside it. So we'll poison your customers, but don't worry. That's what you need to be the best in town. Don't pretend that they're all over it. So anyway, please don't actually put soap filling in your biryani. It won't end well. But anyway, this is our little loop-de-loop. It has a little soap layer. And now what I'm going to do is I'm going to take the 2 wires and put them inside. So like this, and like that, in and out, in and out. And so, this is our loop-de-loop and our 2 wires. So let's just delete these clones. They're not meant to be here. And now we're going to erase this as well. And this is our thing. And our closed loop is this. This doesn't work with an open loop. So the closed loop, and if we take the magnetic field at this point, say here, and this point here. So the closed loop integral of the magnetic field dot, well, dl, we'll say, is this little guy over here. Sorry. And so dl is a tiny portion of the length of our loop. Is going to be equal to mu naught times, well, mu naught times iron cloak, which is basically all the stuff that goes in here. By the way, what you have to do is the loop can flow a certain way. I would say that it goes, well, clockwise for this time. And so this goes clockwise. So now, what is the positive direction? Well, let's see which way my fingers curl. If my thumb is going upwards, then they curl, well, this way. They curl this way, which seems like clockwise. Yep, it goes down, up, which is exactly how my loop-de-loop goes. And, well, if you put it down, then they will rotate anti-clockwise, which is this direction. So you can see that it goes this way when up and this way when down. So it's opposite. Ha! So that means that positive is the positive direction in this report. So up is the positive direction for this plane. So what is iron cloak? Well, it's just the current that goes through our little soap layer over here. And we'll call that I1 plus I2. Well, let's say I1 is going up this way and I2 is going down. So that means that it's I1, well, whatever I1 is, minus the absolute value of I2. So That is the finished equation of Ampere. But wait, there's something missing. What could it be? Well, the thing here is we got dl equals to mu naught times I1 minus I2, but he missed another cause of charge, that is electric flux, which Maxwell did add, giving us the displacement current, and thus the entire Maxwell's fourth equation, the only original one. And this really connects all four. B, E, along with the third one, you can see the connections now. So anyway, those Maxwell's four equations. But now, finally, we talk about our last scientist, Einstein, and then relativity and then black holes. So Einstein published 4 papers in 1905. One of them was special relativity. So special relativity basically said, hey, time is relative, distance is relative, hell, that's relative. All right. So hell, everything was relative. So how is time relative? How is distance relative? Well, velocity definitely wasn't relative. It was constant for light. So velocity couldn't distort. So time and distance had to distort. Well, let's do that right now with a 3-minute approach to it. So basically, we have the Earth and we have an island and we have, oh my God, we have some guy standing on the island. No. So we have some guy standing on the island, and then we have a spaceship. And what I'm gonna do is I'm gonna take mirror, and I'm gonna take laser, and what I'm gonna do now is it's selected, copy, and now I'm gonna, how do I paste? Paste. All right, paste. Got it. Paste, and then what I'm gonna do, I'm gonna move over here. I'm gonna paste again, paste, and that gives me this. So let's say we have a guy in the spaceship. What the guy in the spaceship observes is, well, if this is D, then the guy in the spaceship observes that it takes the time 2D over C for the light to go from one side to another, and so back, and that gives us 1D trip, 2D trip over light speed, and that's the time that it takes for the guy who sees the spaceship as at rest, so T naught 2D over T. But this guy sees the spaceship as moving, light speed. So let's say that this is L, which is the time, which is equal to V times the time it takes for the light to hit one side and then go back, divided by 2. So it's basically just VT over 2. So anyway, now how can we do this? Well, the thing is, VT over 2, now what we're going to do is the light guy sees it had moved, the spaceship had moved while the light had moved. So that gives us D squared plus L squared. And D squared plus L squared. Well, square root it, if you know Pythagorean theorem. So that gives us T for these guys. Well, the guy on Earth is actually equal to 2 square root of D squared plus L squared over C. And so now let's switch these, and I'll just be doing some math, solving for T, as you know. So you can just watch. So C squared equals 4, and we square this thing. And since L is gonna be VT over 2 squared, so V squared T squared over 4, and then divide that by C. So that gives us c squared equals 4d squared plus v squared t squared over, well, c. No, not t, because I forgot. So anyways, now t squared, because I squared both sides, that gives us t squared equals 4d squared over t squared plus v squared t squared over t squared. We cancel these out, giving us c squared equals 4d squared over t squared plus v squared. Now I'm going to solve for t. So no, I don't know about grad tickets. So c squared minus v squared is equal to 4d squared over t squared. I inverse both sides. It's equal to 4d squared over t squared. No, inverse both sides. Now, what I do is I multiply both sides by 4d squared over c squared minus v squared equals t squared. And then what I'm going to do is I'm going to square root both sides. Well, first I got to factor out c squared from this side. So that gives us c squared 1 minus v squared over t squared. And then I square root, giving us t equals 2d square root of 4d squared over c square root. And the square root of 1 minus v squared over c squared. 2d over c is going to be equal to t naught, giving us the equation for time dilation, which we'll call 1 over 1 minus v squared over c squared, gamma. So t naught over gamma. But now we know one part of the equation, but what about the other, length dilation? So v equals d over t. So now we know that v is d over t naught over gamma, which is kind of a tricky situation. To cover for this, what I'm going to do is I'm going to divide d by 1 and then go t naught over gamma. And so now we can use a over b over c over d rule. D over 1 is equal to t naught. Well, no. Gamma over t naught. So we're actually getting nowhere with this. Why? Well, because we're going to use L and L naught to denote distance. So what we're going to do is this is not going to work. So instead, what we're going to do is L naught is going to be V delta T or VT. And L is VT naught. So now we know that L naught is VT. So VT is going to be VT naught over gamma. So actually it's the reverse way around and I'm not paying attention. So that gives us L is actually equal to L naught over gamma. So that is time dilation and then contraction. I don't have much time left. So somebody entered super late because we only have like 15 minutes left in this thing. But anyways, we're gonna talk about black holes. So what are black holes? Well, they may seem mysterious to the average commoner, and that's what we are going to be talking about today. So we have this guy, and I'm just going to put some glow around him for the fields. So here's our black hole. And this may seem mysterious, but do not worry. There's nothing to fear. These black holes are only so strong because of their gravitational field. The gravitational field is what defines the gravitational field is because of their very small radius. So Fg is huge when you have a small radius. So, and it also has a very proportionate mass. So it's like tiny r and big mass equals huge g. So this equation, if based on size, should look more like this. No. Like this. No. Oh my damn god. Like that. Yep. So force of gravity here is huge due to the characteristics of the black hole. So that's the only way the black holes are so really strong. But how do we shape the Earth into a black hole? Well, first we have to make the escape velocity higher than c. So, well, we have to shrink it to a certain radius, which we can measure by, well, let me just do some quick math. Take the integral and leads. No. M over v squared was half v squared. No, why did I write v squared? It's r squared. So we solve for v, we get v squared equals 2gm over r squared. And so we get v equals square root of 2gm over r. So that is the equation we'll use for escape velocity, and radius equation is, well, standing right in the open. So radius is going to be 2gm over v. So now, if you plug in the numbers, you get something reminiscent to this. So that is the number you'll get, meters. So that means that we have to shrink it to 3, actually no, 8.88. So 8.88 times 10 to, no, not 10 again, times 10 to the 10 to the minus third power. And finally, now we know this, and we'll actually plug in, for this, we plugged in v and something right above c, 3 times 10 to the 8. So it's understandable that when we plug all the values back in, we get v is 3 times 10 to the 8, meaning that the escape velocity is higher than the speed of light, which, if you don't know, is 2.997 times 10 to the 8. So, yep. Finally, we have made the Earth a black hole. Hopefully I don't get sucked in. But anyways, that was a pretty long lecture. I actually didn't expect it to be this long. So, thank you all for giving me a chance to talk to you. So now, if you have any questions, I'll wait for 2 minutes. So I have a question session from 9:50, well, right now, for me, it's 9:51. So I'll say from 9:51 to 9:53. So what questions do you guys have?
Dear participants, if you have any questions, you can even put forth your questions, so that either you can put forth your questions in the chat box, or you can just even raise your hand so that I can unmute you. You can even put forth the question to Professor Savannah Sakbari.
I do not want I don't want 75 people speaking at the same time. So I will only accept questions in the
1 or 2 people. We'll get it from 1 or 2 people. So Nanashekaran sir. Nanashekaran sir.
Sir, good afternoon. Levin sir.
Good afternoon. Yes, good evening, sir. Any questions or any other comments that you need to give, sir?
The question is, what are the factors influencing his extraordinary intelligence? Because I was thrilled to see a child prodigy is presenting such a vast and complicated and complex topic. I want to know the factors influencing his the formation itself. What are the factors influencing him to making such a child genius? What are the factors?
Only one. I have a great teacher and a great father. My father is a very great teacher. He even teaches at the university he's at right now. So he's a very great teacher. He's the one who taught me everything actually. So yeah, I feel like he is the one who had a great factor on my life, and he's the one who spoke my curiosity. Now every day I go out stealing stuff from my father's garage and do sciencey stuff in the meantime. And my dad scolds me whenever he comes back home and sees it.
Happy that I want to know what is the approach, what is the approach and attitude of your students around you of your age. I'm talking about the students of your age. What they think about you? Are you a model to emulate for them?
Well, I didn't have. Well, because I haven't really focused too much on the performance of my fellow students and instead focused on the class too much, I don't really get the idea of how they what they think of me. But what time I have seen them, they don't really try and get to my standard, because I mean that's like trying to grow to the Eiffel State Building while only eating hamburgers. I mean, that's impossible, isn't it? You'll die of too much constipation before you ever reach that point.
Fantastic. My last question is: what is your future vision? What do you want to become? What do you want to become? What is your future stock? I want to know what you are going to be in the future. What is the role you are going to play?
Mathematician and math teacher.
Oh.
I think a lot of prominent people have just become math teachers and physics teachers. Didn't Einstein become a physics teacher? So yeah, I just aim to become a mathematician or a math teacher.
Okay. Thank you very much. It is incredible. It is something incredible. Congratulations.
Thank you. Any other questions?
Any other questions, participants, do you have? If you have any other questions, you can even put forth in the chat box so that it will be taken to the resource person, or else we'll go with the end of the session. Okay. So it is indeed a great privilege to have Professor Savannah Sakbari here. Really, I don't know how long the 1.5 hours it went. It is again, I was totally enthralled with this lecturing mode. But he's going on demonstrating with some materials. Immediately he's going on some diagrammatic presentations when he was sharing about all those the very vast areas in the physics. He was talking about Einstein, he was talking about Maxwell, and he was going on talking about many equations. Even at our own age right now, it is very difficult for us when we're sitting in a physics class and going with all these derivative parts in particular. But literally an 8-year-old professor who is enormous in his idea, enormous in his knowledge, and taking all the way, being a world young professor is a great job. I hope so. So on behalf of GJASC Arts and Science College, the entire family members of GJASC Arts and Science College in particular, our beloved secretary, Mr. P. GJASC, our principal, Dr. S. Malarkodi, and the heads of the departments of our institution, as well as professors of our institutions, and from students' behalf and on behalf of the participants. It is indeed a great privilege for us to have you here. Thank you very much, Professor Savannah. Amidst your hectic schedule, you joined with us today. So thank you very much. Thank you, Professor Savannah. And it is indeed a great privilege to thank our father of Professor Savannah, another Mr. Rasidul Bari, who have joined with us also today in this meeting. It is actually the nice essence that what you're giving to your kid, it seems, because I hope none other is role model for him except Mr. Rasidul Bari. He is the only role model for Professor Savannah, I think so, because he is also a teacher by profession, Mr. Rasidul Bari. So when Dr. Anashekhan, a very most senior professor in Coimbatore, he worked there in Tiruchi and then shifted to Coimbatore. Even after his retirement, he was working. So when a senior most professor, when was throwing a question to him, That's what you're going to do in the near future. He was telling that I want to be a math teacher. So many mathematicians are also there. We have Mrs. P. Malati, the HOD of the mathematics of Geeta Arts and Science College. See how an youngster has a burden to become a math teacher. So it is indeed a great privilege to have Mr. Rasidul Bari also with us. So hopefully in the coming days also we'll have more lectures on this, and we'll take the best out of it, what we can go with. So thank you, Professor Savannah Sakbari, and for Mr. Rasidul Bari for accepting the invitation and for gracing the occasion with your great insights into the field of physics. So it is, again, we can say Professor Savannah Isaac as the 21st century Isaac Newton. So that is what the thing that what I felt. I really was enthralled by 1.5 hours what he was going on doing the lecture. So thank you very much again. It is indeed a great privilege to thank the secretary of the institution, Mr. P. a supporting pillar for the programs what are organized in our institution. Next, I would like to thank our beloved principal, Dr. S. Malarkodi ma'am, for being the source of encouragement and motivation in organizing all the webinars and other programs in the institution. Thank you very much, Malarkodi ma'am, beloved principal again. It is indeed a great privilege to thank all the heads of the departments of our institution, professors of our institution, fellow students of our institution, as well as professors, most probably senior most professors and other professors and students, scholars have joined from other various institutions across the nation and globe. Once again, I thank you one and all. Thank you. Thank you all. Thank you. Principal ma'am, you can even give a thank you note to Professor Savannah.
Thank you, Professor. Thank you. We are wondering how intelligence you are having. And we have got a lot of information, and it is a very highful, informative talk. And thank you very much. And we all congratulate you. We cannot express words for praising you. The youngest scientist in the world. We are very happy, and it is a prestige for us also. And it is a very great honor to be along with us for the past 1.5 hours. Thank you very much for accepting our invitation and gracefully delivered a lecture on this topic. Thank you very much, Professor. Thank you.
And thank you, Professor Kumar, and thank you, Madam Principal, for inviting Professor Savannah Isaac. And Dad, I'm sorry that I had to leave home very early in the morning. I saw you sleeping when I left home 6 in the morning. But I was very excited watching you from my work, and I'm so proud of you. And again, Principal Madam and Professor, thank you very much for inviting him to give a talk at your college. Hopefully, we can continue this relationship.
Definitely, sir. Thank you very much, sir. Thank you.
Namaskar.
Thank you, Professor Savannah. Namaste. Thank you. I request the participants to have to switch on the camera so that we can even take a photo snap of this as a memorable occasion.
Hello, good evening all.
I request the participants to kindly switch on the camera.
Good evening all.
I request the participants to kindly switch on the camera so that we can have a photo snap. Probably Rajeshwari ma'am, Nashikta, Sukanya, Uma ma'am, you can even switch on your camera so that we can even take a snapshot.
Sir, some professor is calling you.
Yeah, well, there is some network issues for the Mrs. Jyoti Cassandra team, ma'am.
It's okay.
Yes. Okay. Okay, come on, be fast. Whoever need to join in the photo session, you can even join earlier. So we request the participants to kindly snap as a memorable occasion. Thank you all. Thank you, participants. Thank you. The feedback form has been rolled out in the chat box. You can even click on it and you can leave your attendance and feedback so that it will facilitate us to provide you with a certificate. So we are processing the certificates for the program which we have organized before, and right now also we are moving with the certification process. So definitely you'll get your certificates within a week of period. So thank you all. Thank you again. Thank you.
Thank you. Thank you.
No, thank you.
Thank you, sir. Thank you, Nanashivan sir, for being a part of this program again.
Okay. Thank you, sir. Thank you.
Thank you. Thank you.
Thank you.
Thank you, Professor. Thank you, Professor Savannah. Thank you. We'll end this meeting.